All right, today we're going to pull back the curtain on something you probably use every day but never see. It's this invisible nervous system that runs our modern world, a hidden language that powers everything from these giant factories to maybe even the smart building you're in right now. So let's dive in. Have you ever really stopped to think about it? You've got factories, power grids, smart buildings, all these different sensors, motors, controllers, often from dozens of different companies. How in the world do they all talk to each other? How do they coordinate to actually get things done without just, tripping all over each other? Well, the answer is kind of wild. A huge number of them, a massive number of them, rely on a language that is shockingly simple, incredibly tough, and was invented, get this, way back in 1979. And that language is called Modbus. Yeah, you can really think of Modbus as the industrial world's universal translator. It's the true lingua franca that lets all these different pieces of equipment chat with each other totally seamlessly. So what is it exactly? Okay, the official definition calls it an application layer messaging protocol. That sounds super complicated, right? But all it really means is it's just a set of rules for having a conversation. It's not the physical wire itself, it's the language that's spoken over that wire. It defines exactly how one device asks for information and how another one is supposed to answer. Simple as that. And the beauty of Modbus, and this is the real secret to its success, is just how simple it is. To really get it, let's use an analogy. Let's imagine all the devices on a network are part of this huge industrial library. Now, in this library, there are basically two roles. First, you have the client, and you'll hear this term replacing the older term master. This is the device that starts everything. It's the one with a library card, always asking the questions. And then you have the server, which is the newer term for slave. This device is our librarian. It just listens quietly, waits for a request, and then provides response. And here's the key rule. The librarian never speaks unless it's spoken to first. And this brilliant simplicity, it describes the entire conversation. The client, our person with the library card, sends a request to a specific server, the librarian. The librarian, the server, gets it and goes to find the information. And finally, the server sends a reply back. That's it. A clean, simple, three-step transaction. Done. Okay, so what does one of these requests actually look like? Well, sticking with our analogy, you can think of it as the little request form you'd hand to the librarian. Let's break it down. Right at the very heart of any Modbus message is this thing called the Protocol Data Unit, or PDU for short. This is the real meat of the message, the part that contains the actual request. And what's really cool here is just how straightforward this PDU is. It only has two parts. First, you've got the function code. Think of this as the action verb. It tells the librarian what to do, like read data or write data. And the second part is just the data field, which has all the specific details for that request. Like which shelf to look on and how many books to grab. So what kind of info can our librarian actually go and get? Well, Modbus basically organizes data into four main types, or four sections of the library. You've got simple on-off values, kind of like a light switch you can control, that's called a coil. Or maybe a door sensor you can only read from, that's a discrete input. Then you have 16-bit values, which are called registers. A holding register is one you can actually change, like a temperature set point you're trying to adjust. And an input register is read-only, like the current room temperature reading. See? Super logical. So in a perfect world, the whole exchange is just super clean. The client sends its request, the server finds the data, and it sends a normal, error-free response right back. Boom, done. Simple as that. But we don't live in a perfect world, do we? So what happens if the client asks for a book that doesn't even exist? Or what if it tries to write in a reference-only section of the library where you're not allowed to write? This is where Modbus gets really smart. It has something called an exception response. Instead of just staying silent or crashing, the server sends back a very specific error message. It actually takes the original function code and changes it slightly to signal, hey, there's an error. And then it includes a special exception code that says exactly what went wrong, like a legal data address. It's the librarian politely saying, sorry, can't do that, and here's precisely why. So the key here is, it's not just an error, it's a helpful error. Okay, so far we've been talking about the content of the message, the what and the why. But that's really only half the story. Now we gotta talk about how that message actually gets delivered over a physical wire. For standard serial communication, you can think of Modbus as having two main dialects, or transmission modes. The first one is RTU, which stands for Remote Terminal Unit, and it's by far the most common one you'll see. It's really compact, super efficient, and it sends data as raw binary. It's pure machine talk. The other one is ASCII mode. Now, this one's less efficient because it sends every byte as 2 human-readable characters, but that can sometimes make it easier for a person to look at and troubleshoot. But here's the most important thing. Every single device on the network has to be speaking the same dialect, no exceptions.
So let's take a quick look at that popular RTU message frame. It always starts with the slave address. Basically, who is this message for? Then comes the function code. What do you want them to do? Then you've got the data itself, and it all wraps up with this crucial 2-byte CRC check. That's a powerful little bit of math that makes absolutely sure the message arrived perfectly intact with no errors.
Okay, all of this brings us to the really big question. In a world of incredibly complex, fast-moving technology, why on earth is a protocol from the 1970s not just surviving, but actually thriving? I mean, just think about that for a second. This slide really puts it in perspective. Modbus was born in 1979. That's the same year the Sony Walkman came out. It's older than the public internet, it's older than the PC revolution, it's older than pretty much everything we consider essential tech today. The answer really lies in its core design. First, it's just so simple and elegant. That makes it incredibly easy for engineers to implement on pretty much any device. Second, it's an open standard, so nobody has to pay licensing fees to use it. That's huge. Third, its built-in error checking makes it extremely robust and reliable, which is perfect for critical environments. And because of all of that, it's now universally supported. It is, quite simply, everywhere. And this quote really just sums it all up, doesn't it? A piece of technology from the age of bell-bottoms is helping to run our AI-driven future. It's just an incredible story of longevity when you think about it. And that really leaves us with a final thought to chew on. As we build these ever more complex systems, maybe the biggest lesson for Modbus is that the solutions that truly last the longest are the ones that are fundamentally simple, open, and reliable. In our increasingly complex world, what is the power of simple?